Inequalities via graphical methods. So show that x. Okay. Now we've got to look at inequalities in a few different ways. So we've done it algebraically above. Then there could be inequalities applied in a geometric sense as well as in a I guess calculus sense. Now the biggest one that's been asked over and over again has been obviously calculus based. Now the reason why we've left geometry in there is because the syllabus is so vague. Now you guys know in year 11 and year 12 there is no more geometry, so it's a bit funny. We left it in there just in case. So we're not too sure about this. We'll find out, I guess, this year with this year's students. So right now we're going to look at it in more of a calculus-based approach because that is the stronger method. So inequalities via the graphical methods, it's still almost calculus-based. So you'll see what I mean by that in a second. So you need to understand a little bit about how it works in calculus. Now, before we can do this, I do need to just make a quick point, something that we're about to start in year 12. It is our first topic, but you all need to know it, obviously, for this, so we might as well start explaining that before I continue with this. So there's a thing called stationary points. Right now, stationary points are when your curves are either at the maximum points or minimum points. You used to call this the vertex. So vertex is very specific. It's only for a parabola. A stationary point is trying to say for absolutely anything. It's where it's no longer increasing nor decreasing. In other words, it is stationary. It's flat. So those are the points. Now we can actually work out those points using calculus and without using, axial symmetry or anything like that. To find any stationary points, it is where y dash equals to 0. So it's just where your derivative equals to 0 and you solve. So if I show you a basic case, let's just say these ones here. Now if I wanted to find the stationary point of this, all I've got to do is just y dash, make it equal to 0, solve, and I get that occurs at x equals to 1. And then of course you can sub it back in, 1 take away 2, y equals to -1. And that's what you used to call vertex. So for those who find this easier now, you can do that and you can forget about vertex altogether. You don't even need to use that or your axial symmetry. So it's a more powerful technique. Any questions at this stage? Have I lost anyone? You obviously will be looking at this in more detail in our advanced class, but any questions? No? Okay, good. So taking that into consideration, we're going to start looking at what this is saying. So show that x is greater than or equal to log 1 plus x. This means for all x greater than -1. So for all x greater than -1. In fact, if you want to know what all the symbols are, I'm sure we put it at the beginning of every booklet. I remember we did. There it is. They're all there. Now that one means for all. Okay, so if you ever see an upside down A, it just means for all. All right. Back to it, which just means x, for all x anyways, greater than -1. Okay, and it has to be anyways, because if you guys remember what your logs look like, log 1 plus x means shifted to the left, -1, and then it pretty much looks something like this. So you can't get it for anything x being less than or equal to -1. Anyways, like I said, I want to look at it from a graphical point of view. Cool. So show that x is greater than or equal to log 1 plus x. Okay. So what we do, first step, we find f of x, where f of x, and what we're trying to do is make f of x greater than or equal to 0. We're going to try to prove that f of x is always greater than and equal to 0. To find f of x, it is literally just this take away this. And the reason why that happens because you can see once I subtract, I will be proving f of x, which is this, is greater than or equal to x, which is the same logic as if I had plus this over, I would have proven x is bigger than or equal to log 1 plus x. Do we understand that? So step one, we're pretty much trying to prove f of x is bigger than or equal to 0, where f of x is this particular function. Yes? Any questions at this stage? Okay. To prove a function is always greater than or equal to 0, to prove a function is always greater than or equal to 0, what we need to prove is that obviously the function is never going to be down here, right? Because the y value has to always be greater than or equal to 0. And that's essentially, we've got to prove that it's down here. And there is a way of doing that. And that way is firstly to find the stationary point, so to find the maximum minimum point. And once we find the absolute minimum point, we've got to say that it is the absolute minimum point. So let's see how that works. Okay, f of x is this. We're going to differentiate. Differentiate x is 1. Differentiate log 1 plus x is 1 on 1 plus x, because the derivative over the original, right? You guys know that that's the integral of this goes back to up here. The derivative of this brings you here. And then what we're going to do is make that equal to 0. Obviously, start solving for x. So multiply everything by 1 plus x minus 1 equals 0. Therefore, you get x equals to 0. All right, I'm going to stop there. Any questions at this stage? Okay, then sub in 0 to find your y value. So your y value, or f of x, equals 0. Take away log of 1. Log of 1 is 0, so that should be 0 as well. So far, so good. Rub it out. Let's go up here. Now again, something else that I guess haven't quite learned just yet because we haven't got to it in our year 12. I was hoping to get to it before we were going to get to here, but that's okay. Is to find the nature. So to actually find if it's a maximum or a minimum. And that's not too hard. That is the second derivative. So differentiate once equal to 0. You can find the stationary point. So you'll work out what that point is. Then to work out if it's a maximum or minimum, we can find the second derivative. So we're going to differentiate this again. To differentiate this, keep in mind y dash is 1 minus, I guess, 1 plus x to the power of negative 1. So don't forget your index laws there. So therefore y double dash, derivative of 1 is gone. Bring the negative 1 down is 1. 1 plus x negative 2. Which in other words is this. You can see how I told you guys pretty much almost all your topics in year 12 other than probability will be calculus based. So get ready for it. And then if here, just so again, I'll write a few things. If y double dash is this one, minimum, greater than 0, it's a minimum point. If y double dash is less than 0, it's a maximum point. So I sub in at 0, 0, the point that we just found, our vertex or our stationary point, y double dash equals 1 on 1, which is 1, 1 on 1, plus 0, which is 1. That is greater than 0, so that's a minimum. All right, we're almost there. Think about what you've just said. What you've proven is this. You've said the lowest point, the lowest point is 0, 0, 0, 0. What does that mean about your f of x function? The lowest point is 0, 0. Therefore, it's in the top half. That kind of makes sense, doesn't it? You literally proved that. The lowest point, you actually said it's a minimum even. The lowest point is 0, 0. So therefore, f of x must be greater than or equal to 0. Therefore, x must be greater than or equal to log 1 plus x. Now, I can promise you something, right? This will be in your exam, and I can tell you these ones are going to be a lot easier than the ones we've been doing the last few weeks, because these ones always work the same way. So you're going to find the stationary point, show that it's a minimum maximum, finish it off. So these ones here, usually they're the easiest 3 marks you're going to get in your proof section, because they're stock standard, they don't really change, which is good. So this one here, you got to tick, you got to say done. How do you know this is this method and not the other method? Look at it. Algebra with logs, or trig with algebra. That's pretty much the giveaway. Whereas everything we were doing last time, if you want to see them again, they're all algebraic based. Algebraic, 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 algebraic. Okay, cool. So they're not 2 different things. So you'll get used to that. Go there, go there, go there, go down. Back to it. I just want to, I guess, write this line a little bit better, because right now I just had to write it like this, but you really need to write it a better way. So I'm just trying to, where's the little text? Can I not type? Just want to type, nope. As if there's no typing here. Maybe that's there. Can I type there? Okay, perfect. So this is what I really want you guys to be writing. Let me think. What would be the definition for me to give you full marks? Zero, 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 zero is x equals 0, it is a minimum. 0, 0 is a minimum, but since it is the only stationary point, it is also the absolute minimum. Let me have a think of that. 0, 0 is a minimum, but since it is the only stationary point, it is also the absolute minimum. Beautiful. And then therefore f of x. Okay, perfect. That's exactly what you need to write. And if you don't write that, you might not get 3 out of 3, and you might get a 2 out of 3. So you can't just add the lowest point. You have to actually say 0, 0 is a minimum point, right? Which I think we understand. The thing is, this is also a minimum point, right? That's a minimum, and that's a minimum. This is the absolute minimum. What do you think I mean by that? You just have to use your logic.
The lowest minimum?
It is absolutely the minimum. Does that make sense? It is absolutely the minimum. That's how we think of it. So yes, it is the lowest minimum out of the 2. So you got to say that. You got to. If you don't say it's the absolute minimum, so what if it's the minimum? What if it kept going down? So you have to actually say, because again, you guys are in extension 2. You've got to say it is also the absolute minimum, and then therefore, you know, f of x is greater than or equal to 0. Therefore x. Okay, I think we get it. It's time to do another one. Let's try this one. Again, show that cos x is greater than or equal to 1 minus half x squared for all x. Okay, so again, start with, well, before I actually continue with this, anyone have any questions? All right, start with f of x greater than or equal to 0. That's our pretty much our aim. So that means f of x equals cos x minus 1 plus x squared on 2. Make sure you're okay with that. Cos x minus 1. Okay. I'll just keep going until you guys say I don't get it. Bang, bang. Derivative of cos is negative sine plus 2x on 2. Okay, good one. Equal to 0. Problem. Can you solve sine x equal to x? Can you solve sine x equals to x? So you can't just solve sine x equals to x by inversing sine. It doesn't work like that, right? So there's a little problem you faced here. All right, how are we going to fix that problem? Well, let's think of it graphically. What do we have? We've got sine x, which looks like this. And then we've got y equals to x, which looks like this. X is 1. X is 1.2. Should look like that, if I'm not wrong. Where's my calculator? I don't think you guys need to know the rest of it. Okay, anyways, so it looks something like that. This could have been a little bit over to the left or whatever, but it's not so important. So you can definitely see your first solution, which is x equals 0, right, where they both meet. So you're meant to conclude from there x equals 0 would allow this particular equation to pretty much equal to 0, right? Sine 0 is 0 plus 0 equals 0. So one solution is definitely 0. We will sub it in. So let's sub in f of x now. Cos 0 is, cos of 0 should be 1. 1 minus 1 gives me 0. 0 plus 0 is 0. So I found the stationary point. Now I've got to do my second derivative. So f double dash x. Derivative of negative sine. Derivative of negative sine is negative cos. And then plus 1. Then at this stage, we go at, 0, 0. Sub in 0 into x. What does y double dash equal to? So what does f double dash x equal to if I'm using f double dash? F double dash is negative cos 0, negative cos 0, minus 1 plus 1. It's a point of inflection. Annoying people. All right, so I spoke about only y double dash greater than 0, which is a minimum, and y double dash less than 0, which is a maximum. There is a case where obviously y double dash equals to 0, which we say is a possible point of inflection. What's a point of inflection? Again, think of this graph. That's stationary, that's stationary. Somewhere between them, what needed to happen? It had to move from a sad to a happy. That right there is a point of inflection. Right? Now, if that occurred, that means this whole thing would be wrong. Just so you guys know. So if that did occur, that means everything I'm about to say is unfortunately incorrect, which means it's actually moving from a maximum to a minimum. And that's a problem. So the thing is with points of inflections, they're not points of inflections just because they're equal to 0. You have to actually prove them. To prove them, we got this y double dash table. So prove. And if it fails the proof, that means it's not a point of inflection. If it doesn't fail the proof, that means it is a point of inflection. So what we're hoping is that it fails. For it to fail, these signs will be the same. So that means they're both going to be positive or negative, which means that it doesn't change concavity. That means it's not moving from a minimum to a maximum. So let's see what happens. When x is 0, try a little bit before it. Let's say -1. Try a little bit after it. Let's say 1. Sub it into y double dash. So sub it into here. Minus cos -1 plus 1. That gave me very close to 0. It's like I'm just going to write it 0.00015, but it was positive. At 0, we know y double dash became 0, so that's just 0. And then we'll try it at 1. And it also gave me 0.00015. So also positive, which means it failed. Which we know it needs to, because it can't be a point of inflection. Because if it is a point of inflection, that's a big problem. It contradicts everything we're trying to get through. So it failed. So it's not a point of inflection. Okay, so at this stage, we still haven't said if it is a minimum or a maximum. The problem is you can't use f double dash to actually get out your nature. You've got to do nature using a second method. So you guys are literally learning the whole first topic of Year 12 without even starting it. So that's funny. All right, it's okay. We'll be doing it. I think we're pretty much up to it this week or next week, but that's all right. Nature. The second method of finding nature is to just check its concavity through the y dash table. So that's x, that's y dash. And then all we're trying to do is find what's happening to the gradients, because y dash is your gradients, if you guys remember that from year 11, of the graph a little bit to the left and again a little bit to the right. So there's 0, a little bit to the left, a little bit to the right, but this is y dash. So again, we're going to sub it into here, minus sine x plus x. So I'll go ahead and do that. Minus sine -1 plus -1. That gives me a negative number. I'm just not going to put the thing in for now. And then if this was +1, I got a positive number. And then we know at 0, it equals to 0. Y dash equals to 0. Always the case. So what you've just proven, if I have to draw it for you, that's negative gradient. So slope to the left. That's 0 gradient. And that's positive gradient. In other words, you have just proven that at 0, 0, it is a min. So unfortunately, the y double dash method didn't work for this question. But you've learned a very valuable lesson because these are hard to come by, the ones that failed. So a very good case to see there. Anyways, at 0, 0, it is a minimum, but you've got to make your statement properly. Because since 0, 0 is a minimum, but is also the only stationary point, it is also the absolute minimum. So exactly like above. 0, 0 is a minimum, but since it is the only stationary point, it is also the absolute minimum. So that is absolutely the lowest point. So I'll write statement, and then I'll go f of x greater or equal to 0, which means cos x is greater or equal to 1 minus x squared on 2. All right, copy that down. We'll do 2 or 3 more, but don't stress. All right, let's do another one. Hold on. Let me see if I can find one more. Anyone still copying and wants me to go up? I'll do that one as I. Yeah, we can do all of these. All right, Let's do this one. North Sydney Girls High School. All right. I think they came 4th last year in the States. So let's look at this. Consider f of x. That's nice of them. They've already made it a little bit easier. They've already told you what f of x is. Log x minus x plus 1. Pretty much show that f of x is less than or equal to 0 for all. The symbol that they're starting to use this year is that. For all x is greater than 0. All right. So now we're trying to prove that it's less than 0. Okay, keep that in mind. We're trying to prove f of x is less than or equal to 0. All right, let's follow our steps. So, who wants to work this one with me? Who wants to? We'll just do step by step to see if you actually understand every line. Who wants to try it together? I don't know. No. Queenie, let's do it together. Let's see if we can get it out. And if every line makes sense to you. So, differentiate. What's the derivative of the log x, Queenie?
1 on x.
1 on x minus, and then x. So that'll just be
1.
1. Then at this stage, we're going to find the stationary point. So we'll make this equal to
0.
0. Then plus the 1, and then finish it off. So x equals to 1 is your x coordinate for your stationary point. And then usually it is a point. So what are you going to do at this stage? Sub it back in to find your y value. Right? That makes sense, doesn't it?
Yep.
So log 1 is 0, minus 1 is minus 1, plus 1 is 0. So the lowest point, sorry, I can't say that. The lowest or highest point is 1 or 0 at this stage. Do we agree with that? Then we've got our nature. We need to prove, is this a maximum or minimum? Now, like I said, there's 2 methods, and I'm going to do both methods this time. The first method is x and the y dash table. The second method is just observing y double dash. And if y double dash is greater than 0, then we can say that's a min. If y double dash less than 0, we say if it's a max. If y double dash equals 0, like I said, it's possible. That's a point of inflection. So it's not min nor max, it's changing between the two. But it's possible because you've got to prove it. It's important that we get that. All right, all good. So let's do both methods. X, Queenie, that's 1. You know y dash obviously here equals to 0. You're going to pick a little bit before it, a little bit after. Give me some numbers.
0 and 2.
I'm going to choose 2. The only reason why I can't choose 0 because I know I can't log 0. Only in this case. So 0.5.
Okay.
But usually 0 works. It's just this one. Log. Okay. Then we're going to sub it in. Log half. So log ln 0.5 minus 0.5 plus 1. Negative 0.193. And then you guys just will do 2. And that gave me negative 0.3. We went too far, I think. We went too far, didn't we? Give me 1 second. Yeah, and this. Interesting. Okay. Unfortunately, I don't think I made any mistakes here so far. This one, again, it's not looking like it's working very well. So this one's failing now. This one usually doesn't fail. It's just probably I've gone too large. But we'll see what happens with y double dash. So y double dash. Let's differentiate again. So what are we going to do with this 1 on x? Queenie, we've got to differentiate it.
X to the power
Negative
negative 1, so
And then
negative x.
to the power of negative 2,
Oh, yeah.
because you're going to subtract 1.
Yeah.
All right, and then you get what? Negative 1 on x squared, and then we go at x is 1 and 0. What does y double dash equal to? So sub in x is 1 in here. You obviously get y double dash is negative 1, which means what now? It's less than 0, which we can conclude is a maximum turning point. Do you get that?
Yep.
So then technically, from a graphical point of view, what you've just proven is this. X is 1, y is 0. X is 1, y is 0 there. Technically, you're proving that this is going to happen. The maximum turning point is at 1 and y is 0. Well, what does that mean? So let me write it in a second. So since 1 and 0 is the only stationary point, is the only stationary point, it is also the only absolute max. I just changed it up a little bit just so you guys know. You don't have to be so strict with memorizing the sentence. It's more about the importance of the sentence. So what's the important bit? It's the only stationary point and it's the only absolute maximum that you have. Therefore, I don't know, therefore f of x is what? What are you going to say if that occurs, Queen? Is it greater than 0 or less than 0 all the time? Your function, your f of what, x, your y values are always what?
0.
Yep. And in fact, because the smallest point is 0, it is also equal to 0. Does that make sense? So it is less than 0 because you just proved it, but it's also equal to 0 because it is at that point. And that's it. Fx less than 0, and I think that's what we're trying to prove, don't we? Fx less than or equal to 0. Done. 2 parts. So you can see this time this failed. I tried, but it shouldn't fail. It's just that I've gone too far. If I'd done 0.99, I'm sure it should have worked. Oh my god, you know what I did wrong? I just realized. I realized why it failed. I subbed it into the original. Hold on. So I'll show you guys this again. Sub it into f dash. 1 over 0.5 minus 1. That gives you 1. 1 over 2 minus 1 is negative half. Then positive gradient, 0 gradient, negative gradient. Can you guys see how that's a max as well? So positive, 0, negative. All right, anyone have any questions? Let's try one more. Let's try one more. Show that f dash of x equals this, hence show that ex. If f of x equals this, then show that the derivative is this. Hence show that e of x less than cos x. That's a good question, but I don't think just yet. Then we do it by integration. That's next week. I'll get one. Let's save that. All right. Well, yeah, that's all we just did. Those are the ones I gave you, but all good. Okay, let's do this one. It's all integration. This one. ln x minus ax plus b. That's exactly what we just did as well. There's not many with calculus, that's the problem. Hold on, keep going. Phoenix. Let's see if I can find any in here. No, they're all algebra. No. Alright, I guess we'll just do one more find. It's integrals. Yeah. Show x. X plus 1 on x. X plus 1 on x. Okay. It's okay. Let's do it. So we'll do this one here. X plus 1 on x, I think it was, greater than 2. X plus 1 on x greater than or equal to 2 for all x. Alright, let's try that one. So prove, probably a little bit easier. It's okay, x plus 1 on x greater than or equal to 2. Let's not prove it using the way we were doing last week, which is obviously a minus b squared greater than or equal to 0, a squared minus 2ab plus b squared greater than or equal to 0, a squared plus b squared greater than or equal to 2ab. Let a squared equal to x, let b squared equal to 1 on x. Therefore, you'll get x plus 1 on x greater than or equal to 2 root x multiplied by 1 on root x, and then this cancels out, and you pretty much could have proven that. Let's not do it that way and use calculus. So via calculus. So in other words, we're going to go f of x equals x plus 1 on x minus 2. Again, we're going to differentiate this. 1, and then again, don't forget that is x power of negative 1. So when you differentiate that, it becomes negative 1 x negative 2. Might as well go f double dash here as well before I continue. Differentiate again, bring the 2 down, subtract 1. Okay, for a stationary point, we'll make this bit equal to 0. So stationary point, we'll make y dash equal to 0. So 1 minus 1 on x squared equal to 0. Multiply everything by x squared. You end up with this. So therefore, you end up with actually x equals plus minus 1. So then we're going to work it out at each point. So at 1, y dash, sorry, at 1, y, the y value. At 1, 1 plus 1 is 2, 2 take away 2 is 0. At minus 1, you get minus 1, minus 1, minus 2, minus 4. if I didn't do anything wrong there. Just sub it into your y value, right? So now you've got your points. Then we're going to do y double dash. So f double dash x. So now we're doing nature. At 1 and 0. At -1, -4. Y double dash equals y double dash equals. Alright, y double dash. 2 on x cubed. 2 on 1 cubed. That's a 2 greater than 0. That's a minimum. At 2 on -1. That's -2. That's less than 0. That's a maximum. So right now what I know is that if I was to draw this at 1 and 0 right there, I've got a minimum point. And then at -1, -4, somewhere down here, I've got it being a maximum point. So maximum, minimum. What I'm trying to prove is that f of x is always greater than 0, which it's not for all x. Because -1, did I do something wrong? Why doesn't this not work out? 1 on -1 minus 2 is -4. X is -1, y is -4. It is a maximum turning point. This is at 1 and 0. 1 plus 1 is 2. 2 take away 2 is 0. What just happened? No, that doesn't make sense. Is it a stationary point? I don't think so. I think the graph is like this. X cannot equal to 0. You're going to have an asymptote there. So it won't work for anything less than 0. So it's got to be... Alright, this probably would have had to be restricted. So it doesn't work for all x. It would work for all x greater than 0. As we can probably see. Because there's going to be an asymptote there. You're going to have a left side and a right side. It won't work for all x. Because x can't equal to 0 anyways. Right? You won't have that working out. So it's for all x greater than 0. Will this be greater or equal to 2? Using this proof. The problem with that is the assumption here would be, no, that's fine, for all x greater than 0. So we're taking into account just that one. So we won't need our -1 case. And then since 1, 0 is the only stationary point for all x greater than 0, it is also the absolute minimum. And of course, from that you would say f of x would have to be greater or equal to 0. Everything else has to be above, and therefore x plus 1 on x minus 2 greater or equal to 0. X plus 1 on x greater or equal to 2 for all x greater than 0. Not equal to 0 because you can't equal to 0. Okay. So you can see it gets pretty repetitive with the way to think about it. I'm sure once we wrap around stationary points in nature, the concept itself is not that difficult. All right, I'll leave it there. If you've got any questions, as always, stay back. I'm going to send this across to you guys now. Proofs, desktop, save. Please make sure you'll get that.